Hello guys, this is Siddharth Cap, and today in this video we are going to talk about a scalar field which is responsible for dark energy. In the previous video we have talked about Lambda CDM cosmology, in which we have talked about that the present universe has accelerating scenario in which the whole cosmos is basically accelerating. So in the Lambda CDM model, we saw that there is some cosmological constant exists which is responsible for this kind of an acceleration, and from the observation we have found that this acceleration have equation of a state which is giving you the omega is equal to -1. But in the history of universe we have shown that the universe has gone through different epoch. At the very early time after the Big Bang, the universe has again the cosmic acceleration, which we have labeled is as an inflation, and then after that universe has entered in the radiation dominated phase where the equation of a state is 1/3, and then there is again transition happened. This transition has equation of a state is 0. We are calling it matter dominated. But after that, as the universe has grown bigger and bigger, the universe tends to accelerate, and from the observation now we have that the universe is mainly dominated with dark matter whose equation of state is 0, and there is a very large component of some substance we don't know yet is called dark energy, whose equation of state is -1 or -1.1 or lesser than -1. That is the meaning of it. But the thing is that since the equation of state that we are seeing that different epoch have different equation of state, it means that the Lambda CDM model is not a very well defined thing. We need something called dynamical, which explains the different epoch of the universe, while the Lambda CDM model only gives you some scenario of only late time cosmology. And there is still a problem exists in the Lambda CDM cosmology, like the fine-tuning problem. Some cosmological constant is why it doesn't tell us that the why cosmic acceleration started now only, why didn't occur before time. So we lack of some dynamical scenario from the Lambda CDM model. Because of this, theorists think that this kind of acceleration may be responsible due to some kind of a fluid which has exotic property. But if you are taking some kind of an exotic fluid, this equation of state must be some kind of it has to be some kind of dynamical feature that it may explain the inflation, may explain the radiation or matter or the late time cosmic acceleration. But we have not only cosmology, we have also particle physics, and the success of particle physics relies on the scalar field, because in particle physics there is a Higgs field, and Higgs field have been encapsulated as Higgs bosons, which gives the mass, and Higgs field is basically a scalar field. So we have pretty much evidence that the scalar field exists in the universe. So from the idea of particle physics, so what we cosmologists propose that maybe in cosmology also, or in the ground universe, there exists some kind of a scalar field phi. Let us say we denote it with phi, or any kind of a scalar field which exists, which is responsible for this today's cosmic acceleration. So for that purpose, we need to understand that how this scalar field will actually giving us the dynamics. To understand this, we are taking a very simple way of looking the scalar field, which has some kinetic term and it has the potential. Now, how to actually encapsulate with the Einstein's gravity, But the thing is that whatever the fluid we are taking, we need to have the gravity theory, because everything happens in this space and time, and we think that with this space and time there exists some kind of a field on this space of time which is responsible for dark energy. Therefore, what kind of shape this scalar field should take, or what kind of mathematics it will give us. So for that purpose, we are invoking the quintessence, a scalar field which is quintessence and which is minimally coupled with gravity. What is the meaning of minimally coupled? Means that we are writing some action of this quintessence like this. So this section is basically describing us the gravity. We have already seen the action for gravity, and the minimal coupling means that there is a metric and just we are adding some kind of a field over there. Now this portion is actually showing you the kinetic term of the field. It is similar to writing the Lagrangian for any particle, okay, any particle of the mass. Suppose it has mass m and it is going through the velocity v, and suppose it has some kind of an potential. Let us say maybe it is in potential of Earth's gravity, or let us say it has some kind of an harmonic potential. Okay, so this is the mass and there is a harmonic kind of potential, and it will rolling down through this potential, and therefore it will oscillate around here. So Lagrangian is kinetic energy minus potential energy. We can simply write it. Therefore I can describe for this like mv square minus half mx squared. We can also say that okay, mass is not a very much quantity, not a very great quantity, therefore mass can be 1. So I can simply write that half v square minus half x square. Yeah, correct. But velocity, we know velocity is what? Time derivative, like dx over dt is going to give you the velocity. So I can simply write that this one half x squared. So I can also write it here like this, like dt of x squared minus half x squared. This is just kind of a notation, and dt of x is simply like that. Okay, it is a time derivative, so we can also show with the x dot square minus half x square. So this is the complete classical picture of the particle which is in some kind of a potential having the dynamics, and from here we can extract the equation of motion and all these things, and it will show that it has some kind of an influence, like ma is equal to, will give you like whatever the spring constant or the string. So a block is attached with a string. Okay, it is a string and it has simple motion, or a body is basically attached with a spring with kx square having the potential energy, like here spin constant, or maybe some kx and having some velocity, this one. So that is the same analogy is presented here, that okay, there is a field which exists from the beginning of the inflation, and from this inflation this field is basically rolling down towards this kind of a potential. This potential is some kind of an arbitrary, having some kind of a shape like this, and through which it will show some kind of a dynamics which is responsible for the whole whatever it is. So the kinetic part is very much important, correct? Kinetic part is very much important, and we have chosen here the plus, and it has some negative sign. There is not too much it's just the way it is, because what we are seeing that half x dot square minus half x square, correct? So the time derivative must be having the negative sign with this thing. Now since we are working in the 4-dimensional world, in the 4-dimensional world we say that the universe must be like we have already seen the Friedmann-Lemaitre metric, where we are assuming that universe is pretty much homogeneous isotropic. So the metric thing is ds square is equal to minus dt square plus a square dx square. So here it is negative of sign. Now we are assuming that this field is only depend on time. Okay, so it doesn't because of the homogeneity and the isotropy. Wherever we see the universe is looking pretty much uniform, therefore the field which is actually propagating over this space-time must be only a function of time, and doesn't care about that how you rotate or how we just take the field from one place to another place. The field is still same. So it has some kind of a property that after rotation it will look same. And let us say if I am taking like phi plus, let us say delta phi or something, it doesn't pretty much change. Okay, so that is the assumptions that we have taken here. That is the meaning of homogeneity and isotropy. That field must be isotropic, means that wherever you see it has to be same, and if you just displace the field after with some kind of a coordinate, it doesn't change. So that is the meaning of it. So that's why we are saying that this field is only a function of time, correct? Now we have to find the equation of motion with the gravity, and if we are writing this way, it means that it is coupled with space and time minimally. So if you want to non-minimal coupling is saying that okay, it has some kind of an interaction, like some kind of an F term, which is some metric component like metric component and some kind of a field component. If you are adding another term with this scenario, it will have interaction between metric part and the quintessence part via this kind of interaction. That is the meaning of it. So if you are observing some cosmological thing, and if you are studying the simple thing, let us say you are studying the minimal thing, and from the minimal interaction you say that you extract the data for Hubble parameter, like Hubble parameter, you get some kind of value, and from there if you invoke it, you are getting some different kind of an Hubble value. So what does it imply? It implies that okay, the minimal coupling is not working. One thing. Second thing, that maybe quintessence is not a great field to work with it. So both can be true, like quintessence is not a good field, or maybe minimal coupling is not working. So what you can do, you can invoke a interaction part here. As you can invoke the interaction part, and now you from this F model, like for example, you can just say that R into phi is one kind of an interaction exist, or let us say R over phi, or maybe something you can choose a different form. From different form, you take the observational data and you try to see that what kind of an Hubble parameter locally you get, and from there if you say that okay, now whatever we get it is completely observationally good, therefore you can say that okay, there must exist some kind of interaction. So because interaction exists, so that is the one thing. Or otherwise, if it doesn't parameter, if it doesn't corresponds to H0, therefore you can say that okay, I think the thing is that maybe the field is not working. Okay, so that is a statistical process through which we have to rely on it, correct? And then we can understand all these things. So that is why I have given you the whole picture of this quintessence and how we need to understand. So for an example, we are switching off any kind of non-minimal interaction or direct interaction between field and metric, and what we are going to say that okay, there is some kind of a very minimal interaction exists. So what does it tell that okay, well, field, whatever you want to do your work, and whatever I am going to do my work. Your dynamics will influence me, and my dynamics will influence you, and through which we are trying to understand the cosmic nature of our universe. So let us get started with equation of motion. So here 94 just giving you the matter part. Okay, this Lagrangian is also giving you the matter part. I told you that this field is from the matter. It doesn't show you the gravity part. Okay, gravity is completely determined by Einstein's framework, and this SM we are choosing that field must be corresponds to the matter type, and the matter could be anything. Maybe it has this kind of field structure, maybe the field structure will be different, and based on the matter we want to see the dynamics. Okay, now del phi, as I have written here, del phi is d mu phi, and if you take the g00 component, it will give you phi dot squared, because I told you now what is this, like d mu phi, and if you take only g mu nu, d mu phi, what is giving you that g00 d0 phi d0 phi. Now d0 phi is basically phi dot, okay, and g00 is happen to be -1, so this is phi dot square. Therefore we got the Lagrangian where one component is with negative sign, correct? That is the corresponds to this one. Either you take negative common and like this, correct? So this is the thing that is happening there. And sorry, that is not what I meant. This will be some negative here also, correct? And then now if you take that, okay fine, I want to also find gij, so what you will get di and dj phi. Now we have already seen that this phi is isotropic and homogeneity. Because of this, there is no any spatial derivative exist, so this whole term will go to vanished. That is the simple fundamental rule applying here. So that's why our job is pretty much simplified. Now in order to find the find the equation of motion, what we can do, we can just simply varying this action with respect to phi, the field phi. And if you know how to do the variation, which I will show in the later video, then you can find the equation of motion just like equation of 95. Okay, phi double dot plus 3h phi dot plus dv over d phi is actually giving you 0, correct? So this is it. And now the energy momentum tensor of the field, and if you take this action, and you take the action and varying with g, okay, g mu nu, just like g mu nu, then therefore you will get the energy momentum tensor of the field. This energy momentum tensor, which going to basically Einstein's tensor, as we know the field equation. The field equation is simply telling you that g mu nu is equal to kappa square t mu nu. If you want to know more about it, see my previous video. As you can just click on the I button and you will get everything. Okay, so now what you can see here, you can see that phi double dot is the double derivative of this phi with respect to time plus 3 into h. H is Hubble parameter. We have already told you that what is Hubble parameter. And dv over d phi. This v is not explicit function of time, but it is depend on phi, and phi is also depend on time. Therefore, when you take the derivative of this v, how you can do d by dt into v. Suppose you have this one, okay, so automatically, because dv is only depend on phi and phi is depend on time, so you have to apply the chain rule. Okay, so dv over d phi, sometimes people write in this way, that v prime phi, or sometimes people write this one, that v subscript phi. It means that they are representing the derivative term of the potential. Okay, so you don't have to worry about this kind of things. And now we know that what is the energy momentum tensor of this corresponding field when we are varying the action with respect to g contravariant mu nu, okay, contravariant g. Okay, so from here you have to apply some kind of mathematics at how to varying with this square root, and you will get this kind of thing. And this square root of g is the determinant of the g mu nu metric. So you have to first understand that how to varying this kind of thing. And it is not a very great very much mathematics, but you have to be something like you have to think about it. Now t mu nu, that the way that is kind of defined, d mu phi minus g mu nu half g alpha beta. Now this metric is contracted with this derivative of phi and plus v phi. So from here, if you take this 0 0 component, and this 0 0 component will give you only rho, or you just mixed mixed tensors. It is called mixed tensor. One is contravariant, another is covariant, and this contravariant and covariant will give you, the component will give you minus of rho. And from here you will say that okay, rho is equal to half phi dot square plus v phi. And similarly, pressure is giving you tii, the special components of this one will give you the pressure. Now you may ask that okay, hello, hang on a second, a special component of the field does not exist. Yeah, obviously. This, if you take tii, this component will give you 0, and gij, it is existing. But here, here, because they are separately contracting with this thing, therefore we can take the 0th component of this thing. Therefore phi dot square exists, and v phi is again v phi. There is no problem. That's why we have got the pressure part. And from the Einstein's field, the G00 component, here G mu nu, this one, G, capital G component, Einstein's tensor. This 00 component will give you h square, and Gij component will produce you S dot component. We have already seen that. So what we can see here, we can see from equation 99 and 100 that h square is equal to rho. Okay, and this is the energy density of the field, and 8 pi g over 3 is kappa squared, which 8 pi g is kappa squared, which is in the Planck length. Okay, sometimes people are calling it the Planck length, and from here we have to see that how the things are going to play. So h squared is 8 pi g over 3 into rho, and rho is half phi dot square plus v phi, and h dot is giving you basically a double dot over a, and with this equation of 99 you can find minus 8 pi g some kappa square over 3 phi dot square minus v phi. Okay, so here it is the pressure term. Okay, so minus 8 pi g over 3 into pressure, and this is the pressure of this field, correct? And this is the energy density. Now we can easily find the equation of state and all these things, but the thing is that, okay, how do you understand what it will give? In order to understand the field and whatever thing, we need to first understand the inflation, how inflation have occurred. Now we have already told you that how the inflation have occurred, that suppose the inflation is again due to some kind of a scalar field and there is a minima exist in the field. Okay, so the field for beyond past, it is basically rolling down from here, from above hill, and after some time the rolling is very slow, because the moment it starts rolling, the universe has entered in the inflation, and in the inflation what happens is that the scalar field is responsible for the metric to evolve dramatically very high velocity, means that it has exceeded the speed limit of sound of speed of light. Okay, so the thing is that the moment this field is rolling, and this rolling is very slow. So as this is slowly rolling and come to this minima, then from here minima, this field will again go up, but here it will give an oscillate. So as it will reaches this minima, up to which the inflation has the ending. So this is the some kind of a beginning, and this is some kind of an ending. So up to which inflation has the time span. Therefore the inflation has occurred from minus 43 to 10 to the minus 36 or 33 seconds after the Big Bang. So the field was something like this, and after that it has come to minima just like it, and therefore we are assuming that this potential has some kind of a structure of m phi square. Okay, so it has to be self potential, and this potential is responsible to having some kind of an inflation, and when this field will oscillate, therefore because of this oscillation it produces the particles, and this production of particles is giving you the radiation dominated universe. This is called the period of reheating universe, when the universe start to have so many particles and so on and so on. So after inflation, whatever the things happened, existence of quarks, plasma, gluons, and so on. So this is the period after 10 to the minus 36 seconds, universe has entered to radiation phase. So how this dynamically entered to radiation phase? The answer is here, that it has slowly, very slowly rolled in this hill. So it has to be nearly flat, and then when it starts the minima, then it starts oscillating, and it's giving the radiation period. Okay, so when it is giving us the radiation period, that is the concept, and this field has to be slowly moving, and from there we have concept of slow rolling. Okay, so whenever you will talk about inflation, you will always see this kind of concept of slow rolling and all these things and so forth. So therefore from equation 100 we define the universe accelerates for phi dot is less than. Now so this is the acceleration. A dot, A is a scale factor, and suppose I want to see that okay, universe is accelerating, therefore A double dot has to be greater than 0. Okay, but the thing is that here it is a negative sign. Negative sign means that it is deaccelerates from the classical mechanics equation, correct? So therefore phi dot square minus v phi has to be negative. If it will be negative, then A double dot will be greater than 0. So the thing is that first of all we have seen that phi dot square minus of v phi has to be negative. Now if we are saying that phi dot squared minus v phi has to be negative, what does it imply? It implies that phi dot square by 2 is lesser than potential, as we are seeing also in the inflationary scenario, that this field must be, the kinetic part of the field must be less than, because it is the slow roll. The field is slowly moving through the potential, therefore the potential must be very bigger, so that from this period we can get the inflation, means that the universe is basically accelerating with high amount of speed, correct? Now to give an accelerating solution in the context of inflation and slow roll parameter, we are defining this epsilon parameter. So epsilon is basically normalized with mass Planck, which is 8 pi g and 16 pi, and 1 over v by dv over d phi. Dv over d phi is basically telling you how the potential is basically changing with the field, and then with squared we are defining the epsilon. So we will also talk about inflation in the very great detail after the completion of this whole review, and then you will understand everything. And again we can also define this potential having d2 v over d phi squared, the second derivative, and this second derivative also in such a way that this has to be lesser than 1. So whatever the change in potential, that will going to decide the fate of the universe, and therefore we need to impose the constraint on the potential, that how the potential of the field must change, and from the change of this potential we will understand everything about the universe. Suppose this epsilon is not lesser than 1, it will say that okay, the field is changing its potential very dramatically, so therefore whatever the universe which you are living in, it might not exist. Okay, so there could be any kind of a different universe in the multiverse of this madness. Okay, there could be some kind of a universe which has epsilon is comparable to 1 or maybe greater than 0, so that universe might be something very different, bizarre world. But consequently in our universe, the way we have studied the inflation, we have found out that this epsilon must be lesser than 1, this eta which is describing you the potential, the second derivative of the potential must be lesser than 1. So that has been written. So however, they still provide a good measure to check the existence of a solution with an accelerating expansion. So why we have done it? Because we know we have the concrete theory of inflation, so we want to first try to understand this field in the context of inflation, so that we don't need to think about numerically and so on. Theoretical physics relies on more of the wit, how you gonna think of something. So from the different concept, we've tried to understand our field, that okay, how this will play out. Now we have already seen that okay, this slow roll parameter like epsilon, we can also define it with respect to geometry also, that how the geometry should have played out, because there is a field, and there is a field means that matter component. If the matter is changing dynamically, therefore it will change the space-time also. So the space-time must not change very dramatically. Okay, if this is changing very dramatically, then again the universe shape would be different. So now if the field is not changing its potential shape, it means that it doesn't also change the shape of the metric. Therefore we can define epsilon is equal to minus h dot over h squared. So this is kind of a scalar product and negative, so it has the origin, that why it is explained in such a way. Now this is a good measure to check the existence of an accelerated expansion, since they implement the contribution of both dark energy and dark matter, because metric, where we are saying that the universe has the two major components, dark matter and dark energy. So that is the provide, if you have the metric component h dot over h squared, they will tell you everything about that, because we have no way to encapsulate the matter, the dark matter, that we cannot directly find it, but we can actually measure the Hubble parameter. So from the Hubble parameter we can simply say that okay, if I know the epsilon and if come out to be very slow, then we can say that okay, whatever the 101 approximation, it is very good, it's fine, it is doing fine, and we will understand that how this is basically playing in terms of this late time acceleration. Now, equation of state is defined by the total pressure over rho, and this pressure is coming from the matter, and the matter has phi dot square minus 2v. So half phi square, yeah, they have taken in the LCM. So phi dot square minus 2v and phi dot square plus 2v. Now this omega phi has to be lesser than negative, like there has to be in the form of -1 and so on. So if you want to have this -1, and we have already taken the approximation that inflation happened when phi dot square is less than v phi, so assuming that phi dot square is lesser than v phi, so these two components will get cancelled out, so we will drop it, so minus 2v over 2v, and v cancel, therefore we will get omega phi is equal to -1. So dynamically, basically just imposing the simple thing that kinetic term of the field is not responsible for the acceleration, we get the simple thing that the potential will dominate, and the way the potential will dominate, which is actually giving you omega phi is equal to -1 in the slow roll limit. That is a very interesting thing. Hence, because of this thing, what we can get is that this rho is kind of a very much constant. Okay, rho is very much constant from equation 1 of 3. So from continuity equation, also we have the continuity equation rho dot plus 3h rho plus 3h rho plus p is equal to 0. And if we define such a way that they have the integration form like this, rho is equal to rho 0 exponential minus of integration 3 into 1 plus omega phi dA over d phi. Now if you are assuming that omega phi is equal to minus 1, then exponential to the power 0, and exponential to the power 0 gives you that rho is equal to rho 0, which means that it is constant. Okay, now suppose that it is an stiff matter where omega phi is equal to 1, therefore we have log of a, and exponential to the power minus of log of a will basically give you 1 over a or something like that. Okay, so from here, for different omega phi, we can have different rho, and which is actually giving you this kind of relation that rho will depend on like this. Rho is proportional to a to the power minus m, and m can be varying from 0 to 6. It will not take 0, it will not take 6, but in this between we can have different things. So we have two kind of matter. One is matter, a stiff matter, whose equation of state is 1, and there is a cosmological constant or the response for dark energy whose equation of state is minus of 1. Okay, so omega phi is 1, in which case rho is become a to the power minus 6. So we are thinking that okay, this kind of matter is not, it is extreme case of this thing, that this may exist. Now omega phi can be minus of 1 by third, so minus of 1 by third is there, therefore the acceleration can happen within the range of m, having this 0 m between, so rho to the power a rho minus m, and then put the omega phi here, and from here you can easily calculate what is this. Now from here we can simply say that okay, as the scale factor is maybe time to the power law of time, correct? So if this scale factor is depend on the power law of time, then we can have different kind of, again, interesting scenarios. And from here you can also see that this is the power law of kind of things. Okay, now the accelerated expansion occur where for p is greater than 1. So this acceleration is basically giving you when p is not less than 1 but p is greater than 1. It means that whenever we are seeing the acceleration, that t is greater than great. Okay, so it is also saying that it is a non-linear effect. Okay, because if p is not 1, b is 2, so a2 or a cube or t cube or t4 is actually basically giving you the non-linear effect. Now from equation 10, we have already seen that from equation 10, where is this 10? Yeah, this is the 10. Okay, this is 10 is actually giving you that h dot is equal to minus 4 pi g p plus rho. Now if you add the pressure and rho, therefore your potential will get cancelled out and you will get p, which is phi dot, and this must be negative so that h dot is basically positive. Okay, so something like that. And we are actually we basically omit this curvature term. For an example, now we have already seen that this curvature is not producing enough acceleration, so we have just omitted it, correct? So therefore we have seen that h dot is equal to minus 4 pi g phi dot squared. Okay, and this phi dot squared again is very small, therefore h dot must be smaller than h. Then we found that v phi and phi dot can be expressed in terms of h dot. So from here we can simply writing the potential in terms of completely metric form. So first of all we had the matter component, and now we are actually converting everything in terms of a metric component. So if I know the dynamics of the field, it will give you the shape of the metric and so on. And now suppose I want to understand that how the dynamic or the shape of the metric is affecting the field. So from here we have just converted everything in the another thing. So that's why they are inverse to each other, that if you know one thing, then we can have some kind of an idea of other thing, and with this thing we have already know. So h dot over h squared, in the case of slow roll, this has to be very much less, so it will be minus of 1 over 3, and then this says that the v is approximately flat and so on. Okay, so and phi is equal to h dot over 4 pi g, actually telling you some different stories. So here we choose the positive sign of phi dot, yes, hence the potential giving the power law is corresponds to this one. So if we are taking H dot or phi dot to be positive, okay, so power law expansion of 105 and taking this power law expansion, that what could be the power law expansion, so from there we can express v phi in terms of phi and so on, and we will say that this kind of an potential exists where v naught is the potential and the field phi is evolved with log of t. The above result shows that the exponential potential may be used for dark energy provided that P is greater than 1. So dark energy is responsible not by 1 by phi squared, phi squared, but if you take the exponential form of the phi, just like it, then it is actually presenting you the dark energy component, because they will again then gives you the whole scenario of acceleration. In addition to the fact that exponential potential can give rise to accelerated expansion, they possess cosmic scaling solutions, which is shown in 14 and 160, in which the field energy density rho phi is proportional to fluid energy density rho m. So the thing is that scaling solution means that whenever your energy density of the field, which is proportional to fluid energy density, because suppose that if I am taking also the fluid in the system and the energy density came out to be proportional to rho m. So how they will proportional? So as the density of the field is changing and this change is similar to the change in rho m, we can say that this solution corresponds to scaling type of solutions. So suppose for example, for some region, what we are gained is, suppose that we are going to plot rho phi and rho m with respect to some time, and suppose rho m is like this is the rho m, and again rho phi is also coming out to be like this, then we can say that in this region the solution is pretty much scaling because it is following the same pattern. The proportionality makes it scaled. Exponential potentials were used in one of the earliest models which could accommodate a period of acceleration today. Within it, the loitering universe. Also, there exists a loitering universe. We have to see about loitering universe in 161 and so on. For an example, a loitering universe in the brane world context. So we will also see, we shall carry out a detailed analysis of cosmological dynamics of an exponential potential in the presence of barotropic fluid. Yes, now we have taken the field, this field is corresponds to dark energy, but in our system we have told that the observation tells us that the universe is dominated by two things. One is kind of an pressureless fluid, we call it dark matter, and there is a cosmological constant which is basically giving dark energy. Dark energy is given by this fluid, this field, therefore we must have the barotropic fluid. Okay, so that is the meaning of the barotropic fluid, invoking minimally the metric. The above discussion shows that scalar field potentials which are not steep compared to exponential potentials can lead to an accelerated expansion. What is so? It shows that the above discussion shows that scalar field potentials which are not steep compared to exponential potentials. So it means that the exponential potential, whenever we see that exponential potential, the exponential is how, let us say, e to the power ax or e to the power x is basically increasing like this. So it is kind of an not too much steep. Or suppose we have let us say different kind of an potential, it is also, because if you are giving any kind of ball, it will simply roll it down. So suppose we can construct different kind of potential, like this kind of potential also. So if you take the ball, it will again come down. So if as long as any kind of choice of the field or the potential must be in such a way that it should not be more than steepness, like it does not like this one, like this. So it will not work, because if you take any kind of field, it will simply roll it down, and we have already seen that potential is too much important. So what does it say? It says that is a very important point. Okay, how you gonna construct the potential? It is a very important point. The above discussion shows that the scalar field potentials these scalar field potentials, which are not steep compared to exponential potentials, can lead to an accelerated expansion. So we cannot take different kind of potentials. It has to be very much fine-tuned potentials. In fact, the original quintessence models are described by power law type of potential. So besides the exponential potential, we can take the potential to be power law of type, and this power law must be inverse, that I had told you here. Okay, so that's how something will roll and will reach to the minima, where alpha is positive, m is constant. Yes, where does the fine tuning arise in these models? Recall that we need to match the energy density in the quintessence field to the current critical density. So that is the fine tuning. Okay, so this fine tuning must be that whatever the rho phi is the energy density which is corresponds to this cosmological constant or the present critical density. So if rho phi is dominated in the cosmic late time acceleration, therefore this rho phi must be the match with the critical density, and this critical density has come out to be 10 to the minus 47 GeV to the power 4. The mass squared of the phi is given by, so we can also find the mass of this field. This mass field is d2v over d phi square. This you can easily find if you have taken the object with the spring. Okay, so this has the same kind of a scenario. You take the spring, okay, and attached with same mass. So u is equal to half kx square at the k spring constant. Du over dx is going to give you kx and into 2, and d2u over dx squared is giving you just only k, and this k is equal to m omega squared. Okay, m squared omega squared. So let us say this, we are letting the frequency and therefore the mass. So from here we can simply say that okay, d2v over d phi is going to give you the mass of the field, and this mass of the field come out to be rho phi over phi square, where Hubble expansion rate is given by h square is equal to rho phi over mp square, because we have already this equations. h0 square is, this is the mpl squared plus rho phi. Okay, so they are very much linked with each other. The universe enters a tracking regime in which the energy density of the phi field catches up to the background field when m phi squared decreases to order h squared. So there exists again tracking solution. And what is the meaning of this tracking solution? The universe enters a tracking regime. So when the universe is actually tracking the background fluid solution, like background fluid means that when the solution is happen to be like radiation type and as well as the matter type, therefore we are calling it as a tracking type. Means that the field is basically tracking the background fluid, and if it is actually tracking the background fluid, it means that this has to be m phi square decrease up to h squared. This shows that the field value at present is of an order of Planck mass. So field value, it means that the field value is basically of the order of Planck mass, which is typical of most quintessence models. So in quintessence model, we will say that whatever the phi, so it has the huge Planck mass and so on. Since rho phi is approximately equal to v phi naught, we obtained the mass scale to be rho phi 0, where is the critical potentiality mpl to the power alpha and 1 by 4 plus alpha. Then this constant, the allowed combination of alpha and m. So whatever the m you are going to take, so m and alpha is now constraint. For example, constant implies m is equal to 1 GeV for alpha is equal to 2. This energy scale can be compatible with the one in particle physics, which means that the severe fine-tuning problem of cosmology constant is alleviated. Now this thing is basically dynamical. Okay, what does it say? That 1 GeV can be found in the found in the particle physics, which means that the fine-tuning problem does not exist in the quintessence problem. Okay, and there we have invoked the fine-tuning in the lambda cosmological model. Therefore that was the important problem with the lambda CDM model, which have been now invoked dynamically. Nevertheless, a general problem we always have to tackle is finding such quintessence potential in particle physics. Yes, if you are studying the quintessence, then we have to understand the potential of such quintessence field. And one of the problem highlights in reference 12, the quintessence field must be coupled to ordinary matter. Yes, the quintessence cannot explain everything. It has to couple with ordinary matter, which even if suppressed by Planck scale, and that will gonna suppress a Planck scale, will lead to long range forces and time dependence of constants of nature. So it gives you some kind of an time depending force and long range force which is greater than maybe gravity. So there are tight constraints on such forces and variations, and any successful model must satisfy them. So if you are getting some kind of a time dependent constants and as well as the long range force, these forces must have some kind of constant, that their magnitudes in such a way that it does not exceed something. Okay, otherwise this is actually basically implying the existence of fifth force, and still we have not got the fifth force. That is the problem with this. We have experimentally found out the four forces: gravity, weak force, strong force, as well as electromagnetic force, but there is no any signature till now about the fifth force. But now LHC has started the run with the 7 tera electron volt, so maybe we can find something with this run. So after that, this is one kind of field, and in the next lecture we are going to study about Quintessence field, which is again telling you more about interesting feature of cosmological acceleration. So for that we will see you next time. Thank you very much for this whole lecture. If you are interested, you can join, subscribe my channel, share to your friends. Thank you very much. This is Leonardo Kaf signing out.